Hello everyone, and this is physics. In this video, I'd like to have a conversation about temperature and heat. More specifically, this particular curve, and this is a graph of ice to water. It's the melting of ice to water, and eventually becomes steam up here, but we're not interested in that section. From ice to water. Let's have a look at this graph here for a moment. Along the bottom, the x-axis is time. And on the y-axis, I have temperature. And this is in degrees Celsius. Down here is minus 25 degrees Celsius. 0 degrees Celsius, well, this is the temperature of ice. It's when water forms ice, or vice versa, when ice forms water, this plateau. Going up here, well, this is all water, 100% water. And up at the top, we have 100 degrees Celsius. This is boiling water. And when water changes from water to steam. More specifically, down here, this plateau, this is a change of phase. Let's write that down. I'll get a marker. What's happening here is a change of phase. This is ice. This plateau right here, that's ice. Now, ice is a solid, and over here we have liquid water. That's liquid water. So we have ice. Ice is risen in temperature, it rises in temperature, goes up to 0, then it begins to melt. So this is the change of phase, going from a solid, ice being a solid, to a liquid, change of phase. Once it's a liquid, then the temperature of that water will begin to rise until it hits the boiling point. And there's going to be another change of phase here as well. Change of phase yet again. And this time it's going to go from a liquid to a gas, this being vapor. Liquid vapor, or a gas. So coming back down this way, we have solid ice, change of phase, liquid water. As time goes on and heat is being added to the system, the ice is going to melt. It's going to reach this point here. It's going to begin to melt. Then the water is going to rise in temperature. Then the water is going to boil, and it's going to turn into steam, and what we call liquid vapor or superheated steam. But we're only interested here in the solid line. There are some equations that apply to this curve. Let's have a look at them now. Just going to raise this up. I'm going to redraw that graph. So along the y-axis here we have temperature in degrees Celsius, and along the x-axis is time. Time could be in seconds or minutes, hours. We'll just leave it as empty time. And then we have the curve itself. Oh, we got to put in some temperatures. Here we go. 0 degrees Celsius, that's the freezing point of water, and 100 degrees Celsius, the boiling point of water. Anders Celsius came up with this scale, and that's a video all unto itself. But if we draw the curve now for water, this is for water. This specific graph that I'm drawing here, let's draw in a curve here for water. Let's use blue. Blue is nice color for water. So below 0 degrees Celsius, we have a solid. It's ice. Below 0 degrees, down ice. So let's say down here we have minus 20 degrees Celsius. And what the ice will do when it gets some heat, it'll start to heat up, but it will still be ice. It will still be a solid up until it reaches this point. At this point, the temperature doesn't increase anymore. It plateaus. What's happening here is the ice is absorbing the heat and melting, changing its phase from a solid to a liquid. So this plateau here is a change of phase from a solid to a liquid till it reaches this point. Here we have 100% liquid. 100% water, or let's just say liquid. at this point, and here is 100% ice. So we're installing it solid ice, and it's going to melt. You have a combination of water and ice during this phase change right here. Once it's 100% liquid and you're still adding heat to it, temperature is rising, you're adding heat. It's going to rise up to 100 degrees Celsius and then plateau yet again. So all of this is water. This is liquid water. And then we have this plateau. And here's another change of phases going from liquid water to a vapor. So we go from water to a vapor, another change of phase. Now the equations that apply to this curve, there are several of them. In this plateau, in this slope right here, the equation for that slope right there, for heat being absorbed or released, Q represents heat, is equal to C M change in temperature. That C, that is the specific heat capacity for ice. And I'm going to call this C1. At this change of phase, there's an equation that applies here. Q is equal to MLF. This is the latent heat of fusion. I'll talk about these here in a minute. During this slope, the equation is similar to this one. So the heat required to raise the temperature, Q is equal to C, we'll call that C2. M represents mass, change in temperature. And up in here, another change of phase is similar to this one. The equation is Q is equal to MLV. V represents the latent heat of vaporization. So this is fusion, F-U-S-I-O-N, and vaporization. And this is the Canadian way of spelling vaporization. Latent heat of vaporization, latent heat of fusion. Okay. And these values of C, now they come from a chart. And before I go to that, here's our equation sheet. And you have the equations, equation 30, 31, and the others. And below it are values of C. And this is the specific heat capacities for ice, C ice, C for water, and C for vapor. If you have others, you can look at this textbook. Specific heat capacities for different materials, different liquids. This one is for water. Specific heat capacity, they're in a chart, as you can see here. And I talked about latent heats of fusion, latent heat of vaporization. They also come from a chart. I'm just searching through here to find that chart. Here it is. So this is heats of fusion and vaporization, latent heats of fusion and vaporization. They all come from a chart for various liquids. So if we look at this equation, C is the heat capacity, M represents the mass, the amount of water that's present, mass. I'm just going to roll this up a little bit. Heat capacity, this is heat. That's the heat that's going to be required in order to go from here, this temperature, up to that temperature, or vice versa. And heat is energy, has the unit of a joule. C is mass. No, C is the heat capacity, my mistake. Heat capacity. And this is taken from a chart. And let's see what those units are for heat capacities. It's joules per kilogram Celsius degree. And yes, you may think I've made a mistake here, but no, that's Celsius degree. Again, that's a topic for another video. There's your heat capacity. M is mass in kilograms. And delta T, that's the change in temperature. And to open up this change in temperature, it's temperature final minus temperature initial. Delta T is temperature final minus temperature initial in that order. That doesn't change. You don't flip these around. It's in this order. Temperature final minus temperature initial. And the same applies to this Q for the liquid phase. So we have the solid phase here, the liquid phase. During the change of phases, this plateau, M represents mass. Same mass as this one if you're using that same amount of ice, same mass. And L, liquid heat, the latent heat of fusion or the latent heat of vaporization. So let's look at this one more time. Here's our curve. Oops. Got away on me. And we have our curve. I'm just going to exaggerate on this one here. I'm interested in this part. 0 degrees Celsius. So here we have ice. Say minus 20 degrees Celsius. It's ice. It's a solid. And you take the ice out of your freezer and you put it in a glass and it starts to absorb heat from the atmosphere, and it begins to get warmer and warmer and warmer, but it doesn't melt, it just gets warmer till it hits this part right here. Then it does begin to melt. This is where a change of phase is going to happen. So if I had a beaker, I would have a combination of ice and some water as the ice melts to water. So you have a combination of the two phases in here. So this is a change of phase. And the temperature doesn't rise during this time. And let's have a look at that. Over to my side here, I have a beaker, which I've had here the whole time for the video. And it has some ice in it, and I have a thermometer, and it's got teensy bit of water has melted during the time that I was here. Let's see what that water temperature comes to. I got a thermometer. Let's have a look. Okay. And the temperature there is reading 0. I can't see it there. Temperature is 0.5. To do a little bit of stirring here. As I'm getting the temperature of the glass itself here, it's starting to rise a little bit. There you go. About 0.4, 0.5 degrees Celsius. So that little bit of water technically is going to stay at 0, just like the diagram says. Now, the glass is absorbing heat from the room. Heat is transferring through the glass into the water itself and changing the temperature of the water also. At the same time, the ice is melting and trying to keep the temperature of the water here at 0. So we got these two competing temperatures in this little experiment. But if I had this under insulation, completely sealed, okay, it would follow this graph right here. So the ice would begin to melt, and we'd have a combination of ice and water together in a container. And that temperature will remain at 0. I get this throughout until it completely melts. But of course, there's in reality, we have temperatures on the outside, warm temperatures going in, competing with this. But if I had a stable system, completely sealed, this is the graph that it would follow. And up in here, then, that will be liquid water. And as I continue to add heat, the temperature of the water rises and rises and rises until it finally hits 100 degrees Celsius. Now, I don't have a boiling kettle with me. This will be 100 degrees Celsius. During this time right here, the water, say if I had a kettle, and the water will be boiling and boiling and rough boiling, but the temperature of that water during that boil is still going to be 100 degrees Celsius. It won't go any higher than that. Till eventually it all vaporizes. So if I had this in a container, such that I was catching the vapor, So I have here is a change of phase from liquid to a gas, keeping all the vapors all contained. So I have the two phases here, just like I have here the two phases, the solid and the liquid. And the equations, as I said earlier, this one, Q equals C1, change in temperature. For this one, Q is heat, mass times latent heat of fusion. And for this slope, same equation as this one, different value of C. C2M, change in temperature. And for this plateau, you have a latent heat of fusion. Q is equal to latent heat of vaporization. And this is physics.